Hello everyone, I welcome you all to the 7th lecture of this course. The 7th lecture is on protein and Glyco nanotechnology. So in this lecture we are going to learn protein nanotechnology and its application, and also we are going to learn what is glyconanoparticles and its applications. So in the previous lecture you have understood like how we can use DNA for making various nanostructures for various applications. So in this lecture, like protein nanotechnology, we are going to learn how we can use this protein for making various nanostructures for various applications. So this Lego you might have played in your childhood, okay. So using this Lego you can build car, home or any kind of building, okay. So similarly we can make a peptide Lego. So how we can make a peptide Lego? Using the property of hydrophilic and hydrophobic amino acids. So these hydrophilic and hydrophobic amino acids can assemble in water and it can form like a nanostructures. So that is called as peptide Lego. So the first member of the peptide Lego was discovered from a segment in a left-handed zDNA binding protein in yeast, and it was named as zootin, okay. So here these peptides form beta sheet structures in the aqueous solution. What happens in aqueous solution? In aqueous solution these hydrophobic sites shield themselves from water, and due to which it undergo a intermolecular self assembly, okay. So similar to intermolecular protein folding, okay. So this unique feature of this peptide Lego is they form complementary ionic bonds with regular repeats on the hydrophilic surfaces. So using this peptide Lego we can build several kind of structures. So the first application is we can have a nanofiber scaffold which can be useful for 3-dimensional cell culture, and we can also make nanotubes which is similar to your carbon nanotubes, but it is a protein based nanotube that could be useful for drug delivery applications, and we can also make protein based ink. So let us see one by one application. So how we can make this nanofiber based scaffold? So here we can use a peptide of 16 amino acids which having alternating polar and non-polar, and which forms stable beta strands and beta sheets, okay, and it forms the nanofibers by hydrophobicity, and these matrices are with high water content, okay, and also these nanofibers are smaller in size and it has a smaller pore size which can exactly mimic like your extracellular matrix, and also we can include functional motifs. For example, if you want to incorporate GFP, that is possible, and if you want to load some drugs into these nanofibers, that is also possible for therapeutic applications. So let us see how this nano scaffold, like nanofiber scaffold, can be made using these peptides, and how it could be useful for 3-dimensional cell culture, okay. So here the peptide Lego molecules readily undergo self assembly in water and it forms nanofibers, and these nanofibers join together and form the nanofiber scaffold with the pore size of 5 to 200 nanometer, okay. So one of the very good example is radar 16i, and it has been widely used and commercialized in the name of Pura matrix because of its purity, and when compared to the other traditional biological scaffold like collagen and matrigel, so this protein based scaffold have very good porosity, okay, and also highly biodegradable and biocompatible. So this nanofiber scaffolds contain 5 to 200 nanometer pores with extremely high water content, okay. So they will be used in the preparation of 3-dimensional cell culture, and these scaffolds closely mimic the porosity and gross structure of your extracellular matrix, okay. So it is not only allowing the cells to attach and grow, and it is also allowing the growth factors and other nutrients to diffuse in and out very slowly, similar to your extracellular matrix, okay. So that is why it will be very useful for controlled cell differentiation and also for application in regenerative medicine and slow drug release application. So let us see why we need 3-dimensional cell culture and what is 3-dimensional cell culture. So usually in the lab we grow the cells in 2-dimensional, and in 3-dimensional can be useful for tissue engineering application and also for studying the toxicity of drugs. So when you study the toxicity of drugs using this 2-dimensional, what happens is all the cells will get equal amount of concentration. For example, if you are using 5 microgram of drug, so all the cells will be exposed to the particular concentration of drug. but when you translate this research to your animal model, it won't be successful. So the reason is, inside your body all the organs are 3-dimensional, okay. So if you make a 3-dimensional scaffold that can closely mimic your body condition or in vivo conditions, and we can do the drug toxicity as well as various other applications. So when you add the same concentration of drug, here it is not going to work, because only some of the drug molecules can enter inside and some will attack the cells on the outside. So that is why this 3-dimensional scaffold is very useful for studying the toxicity of drugs and also for tissue engineering application. So in case of tissue engineering, so if you want to replace the damaged tissue, so you need a scaffold, that is support to grow the cells. So this 3-dimensional scaffold, so will replace your damaged tissue or damaged skin, okay. So it will grow, and the porosity is very important because it exactly act like your ECM, that is extracellular matrix. So it permeates the cell to grow nicely on the scaffold, as well as it also allows the nutrients to pass through the pores. So that is why it exactly mimic your extracellular matrix, okay. So and the another advantage of this protein based scaffold is it is highly biocompatible and biodegradable. So it could be very useful for tissue engineering and so for various other applications. So let us see some of the examples. So these are the some of the protein based scaffolds, peptide scaffolds, okay. So here the each molecule is 5 nanometer in length and with 8 alanines on one side and 4 negatively and positively charged amino acids in the alternating arrangement on the other side. So that forms the complete nanofiber scaffold. So when you see this scaffold under the scanning electron microscope, you can see the porosity is between 5 to 200 nanometer in diameter, okay. So which is the right pore size for biomolecular diffusion. So when you see the fibers under AFM, you can see that porosity is very small, like 5 to 200 nanometers, but in case of microfibers or traditional polymer based scaffolds, the fiber diameter will be between 10 to 50 microns and the pore size will be ranging between 10 to 200 microns. So you can see here this pore size is also in the micrometer range and your cell size is also in the micrometer range. So it is not going to closely mimic your body condition because your extracellular matrix is in the range of nano network, okay. So on the nanofiber network your cells are attaching and growing. So when you make the nanofiber scaffold, it will exactly mimic like your body condition. And next one is lipid-like self-assembling peptides, okay. So here we can make lipid-like self-assembling peptides with hydrophobic tails and hydrophilic heads, so which will undergo self-assembly in water. So usually you know that in lipids it have the hydrophilic head and hydrophobic tail. So similarly we can make peptides. So how we can make this? Using the hydrophilic amino acids and hydrophobic amino acids, okay. So these peptides have tunable hydrophobic tails with various degrees of hydrophobicity, and we can also add hydrophilic head. For example, you can use amino acids like aspartic acid, glutamic acids, okay. These are negatively charged hydrophilic head, and if you want to make positively charged hydrophilic head, you can use lysine, histidine or arginine, okay. And these individual peptides contain 7 to 8 amino acid residue, okay, with a hydrophilic head. It can be made up of aspartic acid or whatever I mentioned earlier, and the tail can be composed of hydrophobic amino acids, the hydrophobic amino acids such as alanine, valine or leucine, okay. So the length of each peptide is approximately 2.5 nanometer, which is similar to your natural phospholipids. So and again the another advantage of this lipid-like self-assembling peptide is we can fine tune the size of hydrophobic tail by adding the amino acids, okay. So we can enlarge the size or we can reduce the size. Although these lipid-like peptides have completely different composition, okay, so they share a common feature, okay, that is it will have like hydrophilic heads like 1 to 2 charged amino acids and hydrophobic tails which will have 4 or more hydrophobic amino acids, okay. So even though these lipids are different, but they share this common feature, okay. So let us see some more examples. A6D and V6D. What is A6D? A6D means it has 6 alanine followed by D. D is your aspartic acid. Okay. So you can see here each alphabet denoted by the particular amino acid, and this K is for lysine, A is for alanine, and B is for valine, and L is for leucine. Okay. And when compared to this K2V6, that means it has 2K and 6 valine. Okay. It has 2 positively charged lysines. Here you have only one head, and here you are having 2 positively charged lysine as the hydrophilic head, followed by 6 valines as the hydrophobic tail. So we can make this kind of lipid-like peptides using different kinds of head, also different kind of tail, and we can, by simply changing the amino acid composition, we can extend the size or we can shorten the size. Okay. And this mimic exactly like your phospholipid. So we can also make lipid-like self-assembling peptides which can mimic your phospholipid. So how we can make lipid-like peptides which can mimic like your phospholipid? So we can add an amino acid called phosphoserine. Okay. So if you add this phosphoserine amino acid as a hydrophilic head and alanine or valine as a hydrophobic tail, so it can exactly mimic like your phospholipid. So this could be useful for making the artificial cell membrane. Okay. And they also exhibited similar self-assembly behavior to phospholipids, forming well ordered nanostructures. Okay. So these lipid-like self-assembling peptides undergo self-assembly in water, and it can form even nanotubes as well as nanovesicles with an average diameter of 30 to 50 nanometer. So let us see the another example how to make peptide based nanotubes. Okay. So using this peptides we can make the nanotubes or nanovesicles, and which will be similar to your carbon nanotube. Okay. So here the advantage is this is a highly biocompatible nanotube. So we can load any kind of drug like anti-cancer drug or any kind of drug, and we can use it for therapeutical application. Okay. And also it is biodegradable also because it is made up of protein, so it is not going to cause any toxic or induce any immune responses. Okay. So here you can see here how to make this peptide nanotubes. So how to make it, like you can use that quick freeze sample preparation method. So how do you do it? You can instantly flash frozen your sample at minus 190 degree Celsius. So which will produce a 3-dimensional nanotube. So you can have the peptides in a solution and you can immediately flash frozen at minus 190, that is in your liquid nitrogen. So that will assemble and form this kind of nanotubes. Okay. So if you see this nanotubes under electron microscope, it is showing a open ended nanotubes, and again we can also make a cationic peptides using this A6K. We can make the cationic peptide tubes. So what is the advantage of this having cationic peptides? So it is having like a positive charge, and you know that cells and DNA is a negatively charged, so it can easily combine, and it can be useful for delivering your DNA, or also it can be useful for delivering the drugs to the cells. So that is the advantage. And another advantage is we can also have a green fluorescent protein expressing peptide nanotubes, so you can easily monitor the nanotubes where it is going and how it is delivering the drugs. So it can also act like your theranostic nanoparticle or nanotubes. Okay. And we can also make structures like spherical or vesicles like structure. So how could these simple lipid-like peptides can form this kind of nanotubes or nanovesicle structure? Because it's still the mechanism is not well understood, but people are trying to understand using this computational modeling as well as various computational tools. Okay. So if you understand how it is forming this kind of remarkable complex and dynamic structures, and we can make various structures, and which will have not only biomedical application, it will also have application in the other field also. Okay. So using the tools like bioinformatics and computational biology tools, and once you know the peptide sequence or protein sequence, and followed by that what kind of structure it is forming, so we can do the modeling and simulation, and we can understand what kind of sequence making what kind of structure. Okay. So based on that you can design your own structures using the simple peptide sequence. So let us move on to the other application, that is peptide ink. So we can use that peptides as a ink for writing any arbitrary structures, and when you add the cells it will grow in that particular structure. So this peptide ink consists of 3 important regions. One is ligand, the next one is anchor, and third one is linker. So this peptide or protein inks it can be directly printed on any surface, okay, and it will allow the adhesion of molecules to interact with cells, and it also adhere to the surface, okay. And these peptides have 3 regions, as I already told you. It has a ligand, which is for cell specific recognition, and also linker for physical separation between the surface, and anchor for covalent attachment to the surface. So here the ligand is usually RGD. So in one of my previous lecture I already told you what is RGD. RGD is arginine, glycine and aspartic acid. So this will promote the attachment, cell adhesion, okay, and the linker is usually made up of hydrophobic amino acids such as alanine or valine, and the anchor can be varied. So the anchor can be cysteine residue for gold surfaces. If you want to write it on the gold surfaces, you can use the cysteine, and aspartic acid for the amine surfaces, and lysine for the carboxylic surfaces. So using this peptide ink or protein ink, you can write any kind of arbitrary structures. So usually if you want to make this kind of structures, you have to make the mask or stamp. So simple example is you need a stencil kind of thing. So you need a stencil to write the particular alphabet, okay, and for every alphabet, for example, if you want to write MIT or if you want to write IIT, so you have to make separate stamps or masks for writing such kind of structures. But in this case the advantage is you can use the proteins or peptide as a ink and pen, so you can write any kind of structures, and you add your cells, it exactly grow on the particular structures, okay. So it will grow, and what is the advantage and what is the application is, like we can understand the various neurobiological question. So how the cells communicate and how the cells attach and grow. So we can, lot of unanswered questions in the neurobiology can be understand by using this kind of peptide based ink, okay. So let me explain one more time the peptide ink. What are the 3 regions in the peptide ink, because that is very important. So the peptide ink contains 3 regions. First one is ligand, okay, that is your RGD, and next one is your linker, that is made up of hydrophobic amino acids, and anchor. So anchor is mainly cysteine, okay, in case of gold surfaces. So this peptide ink contains 3 regions. The first one is ligand, that is RGD, so which is useful for cell attachment, okay, and the linker, that is made up of mainly hydrophobic amino acids, and the anchor, which is holding this peptide ink, that is made up of cysteine in case of gold surfaces, okay. I hope you understood what is a peptide ink and what are the components of the peptide ink. So let us move on to the other applications. So how we can use these lipid-like peptides for stabilizing the membrane proteins. So one of the important challenge in the structural biology is to isolate and obtain a high resolution structure of membrane proteins, okay. So the study of membrane proteins will not only enrich and deepen our knowledge of how cells communicate with their surroundings, and it can be also useful for making such kind of effectively sensitive sensors. For example, if you touch the hot surface, you take out your hand immediately, okay. So the membrane protein, it is sending the information immediately to the brain, and you will take out your hand within a fraction of a second. So when you understand these membrane proteins thoroughly, so we can make extremely sensitive sensors, okay? And here we can use the lipid-like peptides which work similarly to your chemical surfactants, and it will protect the membrane proteins from undesirable self aggregation. So as I told you earlier, the main problem in isolating the membrane protein is when you isolate these membrane proteins, it will self aggregate. So to avoid that, we can use the lipid-like peptides, and it will come and protect your membrane protein from self aggregation. So you can isolate and you can study this membrane protein, and you can understand, and then you can make a extremely sensitive sensors for various applications. So let us see the another example, how we can use the protein as a passport to escape from the immune system. So usually if the nanoparticle goes inside the body, our immune system will come and attack the nanoparticle. So our nanoparticle has to escape from the immune system so that it can reach the target location and deliver the drug, okay. So how we can escape this nanoparticle from the immune system? See, here you can see the example. This nanoparticle is not coated with protein, so it is taken up by the immune system, immune cells, okay. and we can make a nanoparticles which are coated with the similar to CD47 protein. Okay. So, if the nanoparticle is coated with the peptide which mimic like your CD47, it can escape from the immune system and it can deliver the drug to the targeted location. And another example is we can use the peptide and protein for making sensitive sensors. So, one of the best known example is you can have a protein nanopores as nano sensors. So, here we can use a nanopore based sensor, and the ionic current blockade occurs when a single molecule is translocated through the channel protein. So, let us see the example. Here we can use the biological protein alpha hemolysin. So, here the biological protein alpha hemolysin present a 1 nanometer diameter pore which makes them ideal candidates for the direction of single stranded DNA. You can see here this example. So, this is your alpha hemolysin protein and which is having 1 nanometer diameter pore. So, we can pass the single stranded DNA through this, and when the DNA pass through this nanopore, there will be a decay in your current, there will be a current decay. So, that can be detected, and this approach it is showing a great promise for development of economical DNA sequencing device. Okay. So, let us see the another example, biomimetic assembly of multiple nanowires. So, we can use the biomimetic assembly methodology, and multiple nanowires with various antibodies can be immobilized on the different location on a electric substrate. Okay. So, let us see how it can be made. So, here you can see here this is a one peptide nanotube and this is another nanotube, protein based nanotube, and these are having an antibody specific for the various antigen. So, this green color will come and bind to this antigen, antigen 1, and this red color tube will come and bind to the antigen 2. Okay. So, when it binds, it forms this kind of structure. So, it is under the AFM, you can see here this cross kind of structure. So, using this kind of approach, we can assemble the peptides and we can make the multiple nanowires. So, which will have a very good applications in making various electrical devices. So, let us see the another example how we can make protein or peptide based stimulus responsive material. Okay. So, here we can make the stimulus responsive nanomaterials which are defined as solid structures which will undergo change with a response to external stimuli. So, let us see the example. Here you can use that apocam ELP. So, ELP is elastin like protein. Okay. So, this protein will assemble into meso microscale particle in presence of calcium, and when you remove the calcium with the help of EDTA, which is a chelating agent. Okay. So, when you remove the calcium, it again goes back to the same apocam ELP monomer structure. That means, in presence of calcium it is forming meso microscale particle, and when you remove this calcium it is going back to the monomer structure. So, this is when you load this kind of particles with the drug or anti-cancer drug or something. So, with the presence of calcium or in the absence of calcium, it can be release the drug, and which can be useful for a stimuli responsive material. So, we have seen several applications of protein based nanomaterials in the previous slides. So, let us see what is glyconanotechnology and how we can use carbohydrate, that is sugar molecule, for various nanomaterial applications. So, this glyconanotechnology is a combination of glycobiology, biotechnology and material science. So, here we can use that glyconanoparticles for various applications. In this lecture we are going to see the biolabeling application, as well as we are going to understand carbohydrate interaction, how the carbohydrate interaction and also carbohydrate protein interaction. And similar to your DNA and protein, we can also use carbohydrate as a stabilizing or coating agent of your inorganic nanoparticles, and using that we can make a very good biosensor. So, in this example, this gold nanoparticle is coated with mannose sugar. Okay. So, this mannose sugar is specific for your wild type bacteria, that is E. coli bacteria wild type, and it is not specific for the mutant. And when you add this kind of nanoparticle, and you can easily identify whether your sample containing wild type bacteria or not. So, here you can see the example. Usually the dispersed gold nanoparticle will be like ruby red color. When the particle aggregate or agglomerate, it will form the purple or blue color. So, using the same principle of SPR, surface plasmon resonance, we can make a biosensors. So, here you can see here this gold nanoparticle will specifically bind to the wild type E. coli. So, when you add this gold nanoparticle, when it bind to the E. coli bacteria, all the gold nanoparticle will be aggregated. So when it agglomerated, it forms this kind of color change, blue color, and if there is no wild type bacteria, it will be dispersed, all the nanoparticles will be dispersed, so it will give a this kind of color. So based on that SPR, we can make a very good biosensors. So let us see the another applications, glyco based quantum dots. So the quantum dots is a semiconductor nanocrystals which will give a fluorescence, depends on the size, and these quantum dots can be coated with this different kind of sugar molecule. Okay. So these glyco quantum dots could be applied in cell biology as a routine tool to analyze carbohydrate receptors. So let us see the example. So this is a sperm, and this sperm will be having different kind of sugar receptors on the head region and different kind of sugar receptors on the tail region. So when you use this kind of quantum dots coated with the different sugars, we can easily understand and study the different kind of cells. Okay. So here in this example, the acetyl glucosamine encapsulated quantum dots, it is binding only to the sperm head, and when you have the quantum dots coated with mannose sugar, and this mannose sugar coated quantum dots, these are binding to the sperm body. Okay. That means depends on the sugar receptors on the cell, these quantum dots are binding. So it can be useful for various cell specific labeling. So let us move on to the other example, that is how we can study the carbohydrate interaction. So here also you can use the metal nanoparticles and coated with the sugar molecule. So if there is a interaction between this sugar, that is carbohydrate interaction is there, when you study under this transmission electron microscope, you can see the agglomerated or aggregated particles under transmission electron microscope, and we can also understand the carbohydrate interaction by ITC, that is isothermal titration calorimetry. So it is a physical technique used to determine the thermodynamic parameters of interactions in solutions. Okay. And we can also check the interactions of carbohydrate by using SPR. As I told you earlier, if the particles are dispersed, it will give a different SPR. If the particles are aggregated due to carbohydrate interaction, it will give a different SPR, and also it will give a different kind of ITC value. When it is dispersed, it will be different value, and when it is agglomerated, it will give a different kind of ITC value. Okay. So let us move on to the other example for understanding protein carbohydrate interaction. So here this gold nanoparticle is coated with, encapsulated with your sugar molecule, and when you add the protein mixtures, the protein will come and bind. Okay. And when you add the protease enzymes, so that will degrade all your unbound proteins, and when you do the centrifugation, you will get the unbound protein plus the protein which bound to the gold nanoparticle, and when you do the mass spectroscopic analysis, you will come to know which part of peptide binding to this carbohydrate molecule and which is unbound free peptides. Okay. So this technique is called as Lind's technique. Okay. Using this, we can understand the carbohydrate and protein interaction. So let us see the same method using a simple animation. So here the nanoparticle is gold nanoparticle, and this gold nanoparticle is encapsulated in a carbohydrate ligand. So when you add the protein mixture and you want to understand out of this which protein is having affinity for binding to this carbohydrate. So you can see here out of these proteins, blue, red and purple, so this blue color protein, it is having affinity for your carbohydrate ligand. So once it bind to this, we can add the proteolytic enzymes, so that will degrade all the proteins. Okay. So the proteins which is bound to this carbohydrate are safe, other than that all other unbound peptides will be degraded using these protease enzymes. So how do you separate these unbound proteins? You can do the centrifugation. So when you do the centrifugation, what happens? So the gold nanoparticle with carbohydrate and peptide, it will be settled at the bottom as a pellet, and the unbound peptides will be in the supernatant. So you can remove that supernatant and you can study under this mass spectroscopy. So you will get, and also you can remove the pellet and again you can study under the mass spectroscopy. So based on that you will get a information what kind of peptide sequence are binding to the particular carbohydrate ligand. So this Lind's technique is very useful for understanding the carbohydrate and protein interaction. So let us see the another example how we can use glycodendrimer for preventing the bacterial infection. So dendrimer means tree like structure. So here we are going to make glycodendrimer, that means here we are going to make sugar carbohydrate ligands in a tree form. So that will have more potent and it will prevent the bacterial infection. You can see here this E. coli bacteria, normally it will come and bind to the host tissues and it will cause infection, but when you have this kind of glycodendrimer, so that will bind to this E. coli and it will block the binding to the host tissue and it will prevent the infection. As the generic structure having multivalent ligand, so it is very efficient in preventing the bacterial infection. So let us see the another example. We can also have the lactose coated glyconanoparticles for anti-adhesive therapy. It can be useful for cancer therapy. Usually the tumor cells will come and bind to the endothelial cells, okay, and the tumor cells transmigrate to the endothelial cells and it will grow, okay. This step is called as metastasis. So how we can prevent this? We can make the glyconanoparticles which can block the attachment of this tumor cell to the endothelial cells and it will prevent the invasion and metastasis. As a summary, in this lecture we have learnt what is protein nanotechnology, and under the protein nanotechnology we have learnt what is peptide LIGO, and using that how we can make various nanostructures, and also we have learnt what is peptide scaffold, and using this scaffold we can use it for various 3-dimensional cell culture applications, and we have also understood what is lipid-like peptides, and using these peptides how we can make nanotubes as well as and how we can use these lipid-like peptides for understanding the membrane proteins, and we have also learnt what are the 3 main components of peptide ink, and also we studied the other applications of protein nanotechnology like drug delivery application, also for sensing application, and under the glyco nanotechnology we have learnt how we can use this for bioimaging application and also for sensing and cancer therapy as well as other applications for understanding the carbohydrate and protein interactions. I will end my lecture here. Thank you all for listening. I will see you in another interesting lecture.